In this lecture, we'll discuss about SR flip-flop. We'll discuss with NAND latch part and NOR latch part also. With the NAND latch part, again we'll discuss with the positive edge and negative edge. And with the NOR latch part also, we'll discuss with positive edge and negative edge. So flip-flop means edge triggered or edge sensitive device. Okay. We can call this circuit also called as edge triggered gated latch. Edge triggered gated latch nothing but flip-flop. But level triggered gated latch is not a flip-flop. Okay, right. So first, this is with the NAND latch part and with the positive edge. This is the diagram. So this diagram same as this gated latch with the positive level. Okay. So in the symbol here we have to keep some that like this triangle symbol. It indicates edge triggered. Okay, right. Okay, this is the latch part truth table. This is the characteristic table. Here only one difference in this here. So here this 0 means positive negative edge. It means it is changing from 1 to 0 transition. Okay, and here 1 means positive edge. So it is changing from 0 to 1 transition. So here these ones we generally represent with a rising arrow. The 0 with a falling arrow. That's the representation for flip-flops. So this one representation and in the symbol, this triangle representation, this will come to the difference between gated latches and the flip-flops. Okay. Remaining everything same. Excitation table same. Characteristic equation table same. So you have to watch this lecture after watching gated latches. NAND latch, NOR latch with positive level, negative level. Okay. Now we'll see with negative edge. NAND only with negative edge. See here for negative edge, here we have to keep inverter in the logic diagram. And here we have to keep a bubble along with a triangle. Bubble at the outside, triangle inside. Okay. These are the differences. This is the latch truth table. This is the excitation table, a characteristic table. So in this characteristic table, here 1 will come. It indicates positive edge. Here zeros will come. It indicates negative edge. Okay. Remaining all same. Excitation table same. Characteristic equation same. Okay. Now we'll see with the NOR latch with the positive edge. Okay. So this diagram changing. Here triangle will come. Okay. This is latch part truth table. So this is same as whatever we did with the positive level NAND. Okay. This is also same. This is also same. Now with negative edge with the NAND. Negative edge with this is NOR. Okay. We'll check once previous also. Okay, NOR. So negative edge with NOR. So here circle will come and here inverter will come. Okay. Latch part and this will be same as a negative NAND. Remaining okay, completed. In this lecture, we'll see the use of SR flip-flop. So ultimately, this flip-flop is a 1-bit storage element. We have to store bit 1 and bit 0. So in the set condition, we are able to store 1 and in reset, we are able to store 0. So it is storing 0 and 1, acts like a memory element, 1-bit memory element. Other flip-flops also giving set and reset possibilities, not only SR. Okay, right. In this lecture, we'll discuss the drawback of SR flip-flop. The drawback of SR flip-flop is when we apply S equal to 1 or equal to 1 and the clock is asserted, we will get invalid output. Okay, n plus 1, qn plus 1 and qn plus 1 bar both become same. Both output should be complementary, no? So it is violating that rule. That's why invalid or unused condition is the drawback of SR flip-flop. To overcome this, we went to JK flip-flop. Okay. In this lecture, we'll discuss about D flip-flop, that is also with the positive edge and with NAND latch part. This is the logic diagram, same as latch, D latch. Okay, just in the symbol we have to keep this triangle symbol. Okay. Next, this characteristic table also same, just latch will work with levels, but this will work with edges. So here 0 means it is working during 1 to 0 transition. Here 1 means it is working during 0 to 1 transition. Okay, remaining everything same. Excitation table same as latch. Characteristic equation also same as latch. Coming to D flip flop with NOR latch part, positive edge only. Okay. This is also same. This is also same. This is also same as previous. Okay. Only in the logic diagram we can see the changes in gates. Okay. Remaining everything same. Now coming to a D flip flop with negative edge with a NAND latch part. Okay. So here in the symbol you will get a bubble outside along with the triangle symbol, and here we get NOT gate that we know. Okay. So here 1 means 0 to 1 transition, 0 means 1 to 0 transition. Remaining everything same. Excitation table same. Characteristic equation same. Okay, now with negative edge NOR latch part, D flip flop, logic diagram will change. Okay, then symbol will be same. Characteristic table will be same. Excitation table will be same. Characteristic equation will be same. So to understand this lecture very well, first you have to see a D latch. If you want to understand D latch, you have to see before lectures. SR latch, SR flip flop, gated, non-gated latches. Those you have to see. Okay. I already uploaded, you can go through. Then you can understand this very easily. In this lecture, we'll discuss the necessity of D flip flop. You know, we get D flip flop from SR only by interconnecting JK and connecting one inverter at suitable place. So this D flip flop ultimately developed for the implementation of shift registers. You know, in the shift registers, the input and output data should be same. Okay, in that case, only D flip flop suitable. No other flip flop will produce same output as input. Okay, in the shift registers, we want to shift that same data, but after some delay from right to left or left to right. Okay, so this D flip flop exclusively implemented for shift registers and for some counters also. Some counters means like ring counter, Johnson counter. Those two counters also called shift registers counters. Okay, there also we use D flip flop. Right. In this lecture, we'll see about JK flip flop with NAND latch part and with positive edge. Okay, here triangle will come, remaining everything same as latch, JK latch. This table same as latch. Okay, latch will work with levels, it is working with edges. Okay, that you have to know. Excitation table and characteristic equation same as latch. Now with the negative edge, with the latch part, NAND latch part only. Negative edge means here bubble will come along with this triangle. Okay, and here inverter. This is same as latch only. Just it is working with edges, that is working with levels. This is same as latch. This is same as latch. Now with the NOR latch part, positive edge, the circuit will change, and here triangle will come. This is same as latch, that is working with the levels, it is working with edges. This is same as latch, this is same as latch. Now with the negative edge, NOR latch part, so here circle and triangle will come, and here NOT gate will come. Okay, so this is same as latch, just that is working with levels, this is with edges. Okay, excitation table and characteristic equation also same. Okay, so if you want to understand this properly, you have to see from starting of the non-gated latches, then gated latches. Okay, SR, D flip flop, then you have to come to JK, then you can understand well. Okay, in this lecture we'll discuss about the necessity of JK flip flop. First we implemented SR flip flop. SR flip flop providing set and reset, we are able to store 1 and 0. Okay, but in SR flip flop, one state is unused state. Okay, invalid state. That we want to make it useful. That's why when we try, we implemented JK. Okay, so the drawback in SR is invalid. So the drawback is overcome by JK. But again, in the JK, whatever the output we are getting, that is not stable. Okay, that is the drawback. It overcome invalid, but it is getting unstable output. Okay, so ultimately we developed JK to avoid invalid state in RS. That's the necessity. In this lecture, we will see the drawback of JK flip flop. So in JK flip flop, when clock asserted and when J equal to K equal to 1, this output changing continuously, complementing multiple times. This is called racing. This is the drawback. To overcome it, we implemented master slave JK. Okay. In this lecture, we'll see the meaning of toggle or invalid state or unstable state or racing. In JK flip flop, when we apply clock is asserted and J and K both are equal to 1, this present state will become toggle in the next state. Okay, but this one won't be like a 1 after toggling one time or complementing one time. It will change continuously, 0 to 1, again 1 to 0, 0 to 1, like that. This one also will change. Okay, so that continuous complementing is called a toggle. Continuous, repeated, or unlimited complement is called a toggle. Here we are showing only one time, but in the reality, it will change multiple times. There is no ending until we on the circuit apply the inputs 1 1. Okay, so output is continuously changing. It is not stable or unstable condition. Okay, they're changing 1 to 0, 0 to 1. That's called racing or race around condition. Okay, this is a drawback only. That is also in JK flip flop. We'll see in further lectures how to avoid this drawback. Okay, we use master slave. We'll see in the master slave how it is avoided. In this lecture, we'll discuss about T flip flop with an NAND latch part, that also with a positive edge. Okay, here you can see triangle symbol compared to latch, remaining everything same. Now this is characteristic table. Now these clock levels are working with edges. In latch, they will work with levels. Okay, excitation table, characteristic equation, same as latch. Now with negative edge, here NOT gate and here circle and triangle symbol will come. So here clock values working with edges. Okay, but in latch it work with levels, remaining everything same. Excitation table, characteristic equation. Now with the NOR latch part, that also with the positive edge, here gates will change and here triangle symbol will come. Now these working with edges. Excitation table and characteristic equation same as latch. Now with the negative edge, NOR latch part, here NOT gate and here circle and bubble and triangle symbol will come. Here it will work with edges. Okay. Excitation table and characteristic equation same as latch. Right. Complete. In this lecture, we will see the necessity of T flip-flop. You know, in counters, we need T flip-flop. For example, synchronous counters, asynchronous counters, mod counters, up counters, down counters. Okay. In these counters, we need hold nature and toggle nature. Then only particular count will happen. Okay. So particularly for those counters, we need T flip-flop or JK flip-flop, but we mostly use T, because in JK, along with the toggle and hold, set to reset is there. That set to reset we don't need in the two counters. Okay, there are some other applications of this T flip-flop also.
In this lecture, we'll discuss the difference between characteristic table and excitation table. So, in the characteristic table, we will determine the next state value from the data inputs and present state. But in excitation table, see here, we will determine the input values, data input values from the present state and next state. Suppose for these present state and next state, what can be the input values? Like that. Okay. In this lecture, we'll briefly discuss about master slave JK flip-flop. There are master slave D, master slave SR also, but we are interested about master slave JK because this flip-flop came to avoid the drawback in normal JK flip-flop, that is racing. Okay, that's why we are interested to know about master slave JK. This is the logic diagram. This master slave JK contains two JK flip-flops. This one at the input side is called the master JK flip-flop. This flip-flop at the output side is called slave JK flip-flop. Why this is called slave? Because this is working based on the output of a master. It's depend on the output of a master. That's why this is called slave. Okay. And this master is a positive triggered flip-flop. This slave is a negative triggered flip-flop. Because we are giving, see here, clock directly to the master, we given positive clock, but same clock we will give to the slave flip-flop through the inverter, so it will become a negative triggered flip-flop. Okay, and one more thing we have to observe here, for the master we removed the feedback, but there is a feedback from slave output to master input, that you have to observe. And here we used NAND latch part. Suppose if I use NOR latch part, the gated part will become AND and the latch part will become NOR. In that case, this feedback connections we have to change accordingly. Okay, that we have to remember. So this master flip-flop will work for positive. This is positive triggered and this is for negative triggered. It means for positive, master flip-flop will respond. It will send input to output. Okay, for pause 2 trigger, slave flip flop will become hold. Okay, it won't respond. Similarly, for negative trigger, master will hold, it won't respond, but a slave will respond, it will send input to output. So with this kind of arrangement, we are able to avoid the racing. That is the logic behind to avoid the racing. Okay, so this master slave flip flop is called a pulse triggered flip flop, because during pause 2 this master is working, during negative slave is working, together in total pulse whole circuit is working. So the final output become the slave output and the input become the master input. Okay, right. In this lecture we'll discuss about flip-flop conversion, necessity of flip-flop conversion, that is why we doing conversion, and we will discuss the flip-flop conversion process also, steps. Okay, first we'll see the necessity. I will give you one example. Suppose I want to design serial adder. I want one full adder and one D flip-flop. I have full adder but I don't have D flip-flop, I have T flip-flop. So in this case, what is the options? What are the options? I have to go and buy D flip-flop. That is one option. And another option is, if I able to convert or utilize that T flip-flop into as a D flip-flop, then I no need to buy. This is the second option. Okay. So the flip-flop conversion is about how to utilize the existed flip-flop by making or converting it into required flip-flop. Okay, that's the intention. So we can do nearly 12 types of conversions. We can do T to D and vice versa, T to SR and vice versa, T to JK and vice versa. Then D to SR and vice versa, D to JK and vice versa, SR into JK and vice versa. Total 12 conversions we can do. Okay. Given or existed flip-flop, two names, required or desired flip-flop. Okay. So now we'll see conversion process. There are three steps. In the first step, we have to mix the characteristic table of required flip-flop and excitation table of given flip-flop. We have to mix both as one table. So here Qn and Qn plus 1, present state and next state, will be common to both characteristic table and excitation table. Suppose if Qn and Qn plus 1, any one or both contain X, in this case the given flip-flop data inputs become X. That is the first step. Now second step, we have to determine the simplified equations for data inputs of given flip-flop. Okay, by assuming required flip-flop data inputs and present state as K-map variables. Okay, then in the third step, we have to draw the given flip-flop symbol, because we have that only, that flip-flop only, na? So we have to take the given flip-flop symbol and we have to make it as required flip-flop from the simplified K-map equations. Okay, so in this given flip-flop symbol, the outputs are present state and its complement. Okay, so in further lectures I will take two examples. I will show each step how to do. Okay, in this lecture we will discuss the conversion process of T into D flip-flop, T to D conversion. Okay, so this is the step 1. I told in the previous lecture, in the first step we have to take the characteristic table of required flip-flop and the excitation table of given flip-flop. So here given flip-flop is T and the required is D. So I taken D flip-flop characteristic table and T flip-flop excitation table, and I mix it together. Okay, so this D Qn n plus 1 become the characteristic table of D. This Qn n plus 1 and T, these will become excitation table of T. So here present state and next state will be common to both. Okay, this is the step 1. Coming to step 2, I told we have to simplify this data input value of a given flip-flop T. Okay, by assuming required flip-flop data input and present state as K-map variables. Okay, so D and Q1 are K-map variables, so we need two variable K-map, and we have to determine the simplified equation for T. Okay, that we have to do. See, this is the simplified equation for T. What is the T value? D XR Q1. It means D bar Q1 plus D Q1 bar. Okay, this is the second step. Now in the third step, what we have to do? We have to take the given flip-flop symbol. What is the given flip-flop T? It will contain T, clog, Qn, Qn bar. I told we have to assume present state and its bar as outputs of given flip-flop. Okay. Then what is this T value? I got D Qn XR of D and Qn. So I take an XR gate, I given D here and I given Qn here. Okay, then it will become as D flip-flop. This is the flip-flop conversion process of T into D. In this lecture, we will see the flip-flop conversion process of JK to SR. Okay, this is the step 1. I told we have to take a characteristic table of required flip-flop and excitation table of given flip-flop. SR is the required, JK is the given. So SR Qn n plus 1, this part will become characteristic table of SR. Qn plus 1 JK will become the excitation table of JK. So here present state and next state will be common. One thing you have to observe here, whenever X came in present state or next state or both, this data input values of given flip-flop become X. See here X, 0, X. Then we have to blindly write XX in the data inputs. Here also 1X. Any one or both is X, then we have to blindly write X in the data inputs of given flip-flop. That you have to remember. Okay. Then second step, we have to determine the simplified equation for this given flip-flop data inputs for J and K by assuming required flip-flop data inputs and present state as K-map variables. So S or Qn become K-map variables, so we need 3 variable K-map to determine J and to determine K. Okay, na? Now J will become S, K will become R. Okay. Then in the third step, we have to take the given flip-flop symbol. What is the given flip-flop? JK. And we have to make it into as required flip-flop by using these simplified equations. So what is the J value? S. What is the K value? R. If I connect like that, it will become as what flip-flop? SR flip-flop. I taken JK, I made it into SR flip-flop. Okay, this is the conversion process. This how to get characteristic table, excitation table, I explained in the flip-flops lectures. Okay, go through that.